Okay, so we're going to keep on working with multiple linear regression, but we're going to move on from matrix notation to be able to just look at the examples. And hopefully now you're more equipped to understand what goes on in the background of every single regression model. So in this particular example, this is auction price data, and the idea here is that you're trying to predict the price of a grandfather clock, and those are again old clocks. And this is basically auction data. So one of the predictors is the age. As you can see, this is the number of years of age of the particular clock, and the number of bidders as a predictor as well. So two predictors, and you're predicting the price of the clock. This particular data set is in Canvas as gfclocks.csv. So you're trying to do this prediction with a linear model. Again, the idea is to predict y using these linear model, beta 1 x1 plus beta 2 x2 plus the error term. Again, this is the deterministic component. In other words, this is the expected value of y, and you have the error term. If you use instead matrix notation to just basically categorize this particular model, then what you would do is just set it out to be equal to y, and this is a vector, so I'll put a line below, and that's equal to x, that's the design matrix x, times the beta vector, so I'll put just a line in there, plus the error term. So again, this x beta is the deterministic component, or the expected value of the y vector. We're going to go ahead, and the first thing that we want to do is test for what we call multicollinearity. Remember, multicollinearity refers to when two or more predictors are very related. And we saw a few examples that that helped us basically determine that if there was too much correlation among the predictors, that caused issues with the parameter estimates and the standard error of the parameter estimates. In this case, age and number of bidders are the two predictors that we have. So we want to test, before we do an analysis, we want to see first of all the relationship of y with the predictors, but also we want to make sure that we look at the relationship among the predictors themselves. So one way to do this is to use the scatter plot matrix. If you use the plot function in R, basically using the plot function and passing in the whole data set as long as the variables are numeric, you will get this scatter plot matrix. And the way to read it is, for instance, if you want to see the relationship between the price, which is the response, and the predictors, you would look at this, either the row or the column. Ideally, you would want to place price in the y-axis, so you would want to see this row instead, which is placing the y value on the y-axis. So if you want to see, for instance, the relationship between price and number of bits, then this is the plot that you would want to focus on. You can see that there is some relationship. It doesn't look very strong. If you had to, imagine, let's say, a line that passes, let's say, through most of the points, then the idea is that you would sort of imagine it something like this. There might be some non-constant variance going on, but as far as we can see, there is some sort of relationship. If we want to look at the relationship between price and age, then we would focus on these. particular place, and this is kind of the relationship that it has, both positive, and those make sense. As the age increases, then we would expect the price of the grandfather clock to increase. I mean, it's more antique. And as the number of bidders increases, so does the price on average. Okay, but you would want to take a look at the relationship between age and number of bidders, and you would do that by either looking at this, that's number of bids and age, or this. Okay, so the nice thing of the scatter plot matrix is that you can see it in multiple ways. You can see it with age in the y-axis, which is this here, and with age on the x-axis, which is this plot here. Okay, you ideally don't want to see much of a relationship, and that's what happens here. If you had to draw, let's say, the best line feed, it doesn't look like there is a relationship at all. So it looks mostly sort of flat, and that's what you would want to see. It doesn't happen often. Most of the times the predictors are very correlated. We don't, that usually doesn't cause any problems, but sometimes when the correlation is too high, that might cause issues, right? We are going to see later on how a model is represented in 3 dimensions. So instead of having a line, so in all of these cases here, we're seeing how each individual variable predicts the price. But when you put those together, what you get instead of a line is a plane. And the plane basically looks like this. The plane now is your prediction. So in other words, this plane is just that y hat, which is equal to b0 plus b1 times x1 plus b2 times x2. This now is a multidimensional plane. I mean, it has a slope for the variable age. It has a slope for the number of bits. And then we have the predicted price on the y-axis. So you can see that the plane is trending upwards, which means that as the age increases, so does the price on average, and as the number of bits increases, so does the number of bidders increases, so does the price on average. And also you can see the concept of residuals when you have the actual point and compare it to the predicted point. Now remember that prediction is now a plane as opposed to just a line. So what we will see is that, again, this is a very easy example because it has just predictor number 1 and predictor number 2. So 2 predictors makes it possible for us to visualize. But when you have more than 2 predictors, then a graph like this doesn't make sense because you would not be able to plot it in 3D. The regression output just gives us this, and I just wanted to review a little bit the interpretations of the estimates. And what we would say is that as age increases by 1 year, then on average the price increases by about $12. As the number of bidders increases, then on average by 1, then on average the price increases by about $86. And then the intercept, if the age of the clock is 0 and the number of bidders is 0, then on average the price is negative, minus 1,338. The other thing that we want to see is RMSC here. In RMSC, the interpretation is the same. So on average, the predictions are off by about $133.5. The rest of the statistics are pretty much similar, but we will focus mostly on a couple of concepts, and one of them is the adjusted R-squared, and the other one is the F statistic. Or I think we will do that by the next section.